Welcome back, everyone, to complex analysis. So last time we defined the derivative of a complex function, which again was very similar to what we saw back in calculus, except now we have a complex flavor to it, right? We're dealing with complex numbers. So today we're going to talk about the inverse function theorem, which is another thing that you'd see in calculus, although I don't know if they called it the inverse function theorem. They may or may not have. But in any case, the inverse function theorem back from calc was dealing with, well, how do you take the derivative of an inverse function? So if you have f inverse, what would its derivative be? And you showed that there was a formula, which is basically 1 over f prime of f inverse. Okay, I'm being really, really hand-wavy with that. But in any case, in complex analysis, we have a similar, well, pretty much identical formula for this, which is what we're going to see at the very end of this video. But in any case, what I want to focus on more is something that's going to be seen in probably most of the rest of your upper division classes, and that's inverse functions and this idea of one-to-one and onto, which hopefully you've all heard of in some capacity. But that's going to be the primary drive behind this video, though, is inverse functions. So let's go ahead and get to it. So first of all, hopefully everyone remembers, like, what is an inverse function? Inverse functions are trying to go backwards, right? So if f of x takes x to y, or if f takes x to y, okay, the inverse function would want to go backwards. It would take y to x. Okay, so inverse functions are trying to switch your inputs and your outputs. Okay, and hopefully you all remember that not all functions have an inverse, right? If you the only way you can have an inverse is if you're what's called bijective, okay, or one-to-one and onto. So for instance, the function f defined by x squared, where you consider this function as going from r to r, this function actually doesn't have an inverse when defined like this. Now you might be like, wait, x squared, I know the inverse of that, right? It's square root of x, because how do you undo a square? Well, you just take the square root, right? Well, that's technically true, but we just have to alter our domain and range here. Okay, so to do that, let me sort of walk through how you would go about that. So here's x squared on r to r. Okay, and so notice a couple of things. First of all, notice that the range is not all of the real numbers, right? X squared, okay, only outputs non-negative numbers. Okay, notice how all the y values here are all above 0, and including 0 there at the vertex. Okay, so the first thing we have to do is restrict the range to 0 to infinity. Okay, so let's chop off the negative y-axis here. Okay, another problem with x squared, if we allow its domain to be r to r, is the fact that it's not one-to-one, meaning that it can take two different x values to the same place. So consider 1 and negative 1, right? If you plug these into this function, what do you get? Well, negative 1 squared is 1, and 1 squared, whoops, no negative there. 1 squared is equal to 1. Okay, so what does this tell you? It tells you that f of negative 1 is equal to f of 1. Now the issue with that is, well, if you think about inverses, what would inverses do? They would try to take the output and send it back to the input, right? But this would be bad. For functions, remember, functions can only take one thing and send it to one thing as well, right? It can only take an input and send it to one output. Okay, so if you try to define the inverse function, it would break down because 1 in this case would be sent to both 1 and negative 1, and it would break the rules of functions. So what we have to do is not zoom in. We have to chop off some of our parabola, so we're going to restrict our domain to 0 to infinity. Okay, so when we restrict both our domain and range to 0 to infinity, then the function f of x equal to x squared now has an inverse. And what is that inverse? It's what we know and love, and hopefully we know this in our hearts, deep in our souls. It's the square root of x. Okay, but broad strokes, though, for a function to have an inverse, okay, two things need to happen. It needs to be one-to-one, which is this idea that it only takes unique inputs to unique outputs. And then onto means that everything in its range or codomain is being hit by the function or is being outputted by the function. Okay. Let's get a little bit more precise with that. All right, so one-to-one and on to review. So hopefully you've seen this. If you've taken pre-calc here, you've definitely seen one-to-one, at least on to. You may or may not have seen. If you've been in 322, you've definitely for sure have seen it. If you've taken abstract algebra, you probably have seen it. But in any case, let's go ahead and review this. Okay, so in complex land, we're going to go ahead and start with G and H. And let's suppose that these are open subsets of C. Okay. And let f from G to H be some kind of function. Then we say that f is one-to-one if and only if f of z equal to f of w implies that z is equal to w. So what this is saying is if f of z was equal to f of w, meaning 2 points got sent to the same place, well, this means that they had to be the same point to begin with. Okay, so again, just reiterating, if f of z equals f of w, which means the function f sent z and w to the same place, well, if your function's one-to-one, that means that your inputs had to be the same to begin with. Onto. So we say that f is onto if and only if for every h, okay, so for every element in your codomain or your range, okay, there exists a g in G, so there exists some input such that f of g is equal to h. Okay? So basically everything in your codomain is being hit by the function, or it's an output of your function. So every element of h, oops, and this is our codomain, i.e. our codomain, is an output. Okay, and then finally a function that is both one-to-one and onto is what we would call a bijective function. And the reason why we like bijective functions is bijective functions have inverses. Okay, so we like bijective functions. That means we can go backwards and we get a function out of that process. Okay, so let's go back to calculus for a second and let's go back to our functions f of x equal to x squared. Okay, and let's also consider the function f of x equal to x cubed. Okay, so we have our quadratic parabola and we have our cubic function. Okay, so like we just said, x squared, if we think about this as a function from r to r, now let's pretend like that parabola actually hit the x-axis there. But if we consider this a function from r to r, this was not bijective. Okay. However, the function x cubed is bijective. Okay, so the cubic function looks like this. Okay. Notice it passes the horizontal line test. So if I draw any horizontal line, it'll pass our graph at once, or at most once, I should say, which means that it's a one-to-one function. Okay. Additionally, notice that every single y value is being hit by our function, or it's an output of our function. Okay. So that means that it's onto as well. So this is an example of a bijection. Is a bijection. Now, I didn't actually prove these rigorously, which we're going to get into when we start talking about some complex functions, but in any case, these are functions that we had back in calculus. We had x squared, if we consider it from r to r, not bijective, and we have f of x equal to x cubed. If we consider that from r to r, it actually is a bijection. All right, everyone, so let's go ahead and consider the complex analog to the cubic function, which is f of z is equal to z cubed. Get out of here. So this actually turns out to be a function that's not bijective. Remember, f of x equal to x cubed was a bijection, but in complex land, f of z equal to z cubed actually isn't a bijection because it's not one-to-one. Okay, now to see that, consider the following. So if you plug -1 into this function, what do we get? Well, we get -1 cubed, which is just -1. And if we plug in, now this is going to seem kind of strange, if we plug in 1/2 plus I square root 3 over 2. I'll let you guys calculate this on your own, but after doing some algebra, and in this case foiling, you'll also get negative 1. And so clearly, negative 1 and 1/2 plus I square root 3 over 2, not the same number, right? Now let me go into how I got these numbers, by the way, because you might be like, how did you come up with this? I didn't just think about, randomly, I didn't randomly choose negative 1 and for some reason 1/2 plus I square root 3 over 2. The way I came up with these numbers was thinking about the other representation that we have for complex numbers. Remember, we can think about complex numbers as r e to the I theta. Remember, this is the exponential form, or quote-unquote polar form, if you will, where e to the I theta is equal to cosine of theta plus I sine theta. Now remember, just back from trigonometry, cosine and sine are periodic functions, right? Which means that they repeat every 2 pi, right? They repeat the same values every 2 pi. So right off the bat, I'm a little skeptical when it comes to at least this being injective, because I know that I have some cosines and sines involved. Okay, so the first thing I did to find negative 1 and 1/2 plus I square root 3 over 2 is I just thought, well, first of all, let's go ahead and make R1 just to make my life easier. So I just considered e to the I theta. Okay. Now the next thing I did, well, I thought, well, if I plug e to the I theta into our function, what are we going to get? We're going to get e to the I theta cubed, which, just using our exponential properties, we know that that's going to be e to the I 3 theta. Okay. And then I thought of, well, what are 2 angles I could plug into this so that I would actually end up landing in the same place? Okay. Well, since I'm multiplying by 3, what I chose was, well, let's pick theta equal to pi over 3, okay, which will give us e to the I pi over 3, and then we plug that into f, we're going to get e to the I pi over 3 times 3, which is just e to the I pi. Okay, so that's going to be a complex number with length 1, because we have a 1 secretly in front of that I, whose angle with the positive real axis is going to be pi. So that's going to land us right here at negative 1. Okay, so then I thought, well, what's another angle I can plug in there that'll land me in that same place? Well, let's consider theta equal to, well, just regular old pi. Okay, so if I plug in e to the I pi, okay, and sorry, I'm drawing over my graph here. We're going to get e to the I pi times 3, which is just e to the I 3 pi. Okay, so now this is a complex number who has length 1 and makes an angle 3 pi with the positive real axis. And so if we think about that, I'm going to use a different color here. Where is the angle 3 pi? That's 2 pi, and then 3 pi will land us right back here. So I know I've gotten to the same place. Okay, so what this is telling us is that, let me get my different color out. This is telling us that f of e to the I pi over 3 is equal to f of e to the I pi. And so we know right off the bat that this function is not 1 to 1. Now if you're like, wait, how did you get negative 1 and 1/2 plus I square root 3 over 2 though? Well, remember, e to the I theta is equal to cosine of theta plus I sine of theta. So e to the I pi over 3 is equal to cosine of pi over 3 plus I sine pi over 3, which, using our trig knowledge, this is equal to 1/2 plus I square root 3 over 2. And then e to the I pi is equal to cosine of pi plus I sine of pi. Now remember, sine of pi is 0 and cosine of pi is negative 1. So this leaves us with negative 1. So that's how I got my 2 inputs there. Okay. Now the reason why I'm explaining this and going through this in super detail here is because this is an example where different representations of complex numbers actually gave us an advantage. Thinking about complex numbers rather than our sort of standard quote-unquote form, I thought about it in exponential form, allowed me to sort of deduce that this was not 1 to 1. All right. However, this function, even though it's not one-to-one, it is still surjective, though, or it's onto. So let's go ahead and prove that. Okay, so to prove it's onto, okay, let's go ahead and let's let, I don't know, let's come up with another letter. Let's let A be any complex number, okay? Now to show f is onto, what we need to do is we need to find a, let's say, z in C such that, actually let's not use z, let's use b so that we're not abusing notation there. Let's find a b in C such that f of b is equal to a. Okay, so how do we do this? Well, let's take a, and we're going to kind of follow in the exponential form like we did with one-to-one. Let's write a as r e to the I theta. Okay, now let's think, what's a number that we could plug into f to get this as our output? Okay, so if you think about it for a little bit, let's let b be the cube root of r times e to the I theta over 3. Okay. And hopefully you see where I'm getting this, by the way, because we're going to plug it into the cubic function, right? So that's why I kind of want to do this. Now let's see. So consider this as our b. Okay, then f of b is equal to f of cube root of r e to the I theta over 3, which is equal to, since this is the cubic function, cube root of r e to the I theta over 3 cubed. And if we simplify this expression, well, cube root of r cubed is just r, and then with our exponential properties, e to the I theta over 3 cubed is just going to be, well, e to the I theta. And what's that equal to? That's a. Okay, so our function f of z equal to z cubed is not one-to-one as we showed earlier, but it is still onto, though. So we still have a what's known as a surjective function. But all in all, though, this is not bijective anymore. Let's look at f of z squared. So this is still not bijective, but what is actually kind of surprising with this function is it's actually surjective now. Whereas when we remember our f of x equal to x squared, our parabola, that's not, it was not surjective onto all of r. But this actually turns out to be a surjective function. So let's go ahead and prove that. Well, one-to-one, this is actually super nice. We can use our calculus experience from this. It's not one-to-one because f of 1, and remember, 1 is a complex number, f of 1 is equal to f of negative 1, because 1 squared is equal to negative 1 squared. Okay, however, 1 is definitely not equal to negative 1. So not a one-to-one function. Boom. So we can actually use our calculus experience to prove that. Now, why is it onto? Well, we're going to do the same exact thing we did with z cubed. So let's let a, b, and c. We want to show there exists a b in C such that f of b is equal to a. Okay? So again, we're going to write a as r e to the I theta. Okay? And let's consider b equal to the square root of r e to the I theta over 2. Okay? And again, hopefully you recognize why it shows square root of r and theta over 2. It's because we have z squared here. We're going to square this eventually. So then f of b equals f of square root of r e to the I theta over 2. Now by definition of our function, this is going to be equal to square root of r e to the I theta over 2 squared. And after simplifying this expression, we'll get r e to the I theta, which was a. And so this is an onto function. So it's kind of crazy, right? We have two functions that we are really, really comfortable with are in real land, right? X squared and x cubed. X squared was not a bijection. It was not surjective or injective. And then we had z cubed was a bijection. But in complex land, everything sort of got not flipped, but everything's sort of strange, right? F of z equal to z cubed. This turned out to be a surjective function still, but it wasn't injective. And now z squared, okay, is not bijective. It's still not bijective, but it is at least surjective now. So it's sort of got an upgrade going to the complex, into complex land, I should say. Kind of cool. Now, really quick, if you're curious, what is a function that is bijective? We'll see some examples later, but I'm just going to give you just a slightly really easy example. F of z equal to z, this would be an example of a bijective function. Remember the identity function, f of z equal to z? I'll let you guys prove that on your own, but that is an example of a bijective function. So there do exist bijective complex functions, and we'll see more later, but just to give you something for right now, there's a bijective function. And now really quickly, let's talk about the inverse function theorem. So suppose g and h are open sets, and let f be a function from g to h, and let's suppose that f is a bijection. Now remember, what is that giving us? That's telling us that f has an inverse. Okay. Now instead of calling it f inverse, what your book does, we're going to call it g. Okay, so since f is a bijection, it has an inverse, let's call it g from h to c. I'm sorry, h to g. Okay, and let's let z naught be in h. Okay, so if our function f is differentiable at g of z naught, and let's suppose that f prime of g of z naught is not equal to 0, and that g is continuous at z naught, then we know that the inverse g is differentiable as well at z naught, and the formula for the derivative of g is equal to 1 over f prime of g of z naught. Okay, so let me just write down really quick for you. This was our calculus inverse function theorem. Instead of using z's, I'm going to use x's, because we never really use z in calculus. Okay, so again, virtually identical, except now we're using z's because we're in complex land. And your book, instead of writing f inverse, they chose to go with just g, which is fine, right? Because we could always change the names of our functions. But in any case, we still get the same result that we had back in calculus. We still get an inverse function theorem, meaning if your function's differentiable and it has an inverse, then you can find the derivative of the inverse by using this formula here. All right, that is it for today. So next time we're getting into a really, really cool result of something that you don't really see in calculus, and that's the Cauchy-Riemann equations, which relates the derivative to sort of the partial derivatives if we think about a complex number in terms of its rectangular coordinates. I'm not going to spoil any more than that, but it's a really, really cool and awesome complex analysis result. In any case, I'll see you.